In 1970, the Soviet Space Agency had a problem. Cosmonauts were landing in Siberian swamps where no helicopter could reach them and no tracked vehicle could cross. The ground wasn't solid enough to support anything with wheels or tracks. It wasn't water either. It was something in between, and it defeated every conventional vehicle they had. Their solution was a machine with no wheels, no tracks, and no contact with solid ground at all. It moves by rotating two helical screws. And here's what makes no sense. The softer the terrain, the faster it goes. Siberian swamp terrain is not mud over solid ground. It is a semi-liquid matrix, part water, part decomposed organic material, part suspended sediment with no load-bearing capacity at any measurable depth. A person standing on it sinks. A tracked vehicle, despite distributing its weight across a surface area many times larger than wheels, sinks faster. Not because it's too heavy in absolute terms, because the substrate has no yield point. There is no layer beneath it that stops the sinking. The vehicle doesn't get stuck. It gets consumed. This is the terrain Soviet cosmonauts were descending into. The Soyuz re-entry capsule used a ballistic trajectory that gave ground controllers limited influence over the final landing zone. Siberian tundra was within the calculated landing ellipse for multiple missions. In autumn and spring, when the freeze-thaw cycle left vast regions in the semi-liquid state that defines the worst-case recovery scenario that was not a theoretical risk. It was a recurring operational condition. The recovery window after landing was measured in hours. In Siberian autumn temperatures, hypothermia exposure for a cosmonaut in a damp landing suit begins within 30 minutes of capsule egress. The mission doesn't end at re-entry. It ends when the crew is recovered. And the crew could not be recovered if no vehicle could reach them. Helicopters were the primary recovery platform. But helicopters require a landing zone with enough surface resistance to hover extract a person without rotor wash, creating a vortex over liquid substrate, a condition that makes stable hover impossible at low altitude. In high wind or low visibility, helicopter recovery became non-viable entirely. The Soviet space program needed a ground vehicle capable of crossing terrain that no ground vehicle had ever successfully crossed. The standard engineering response to soft terrain is to reduce ground pressure, the force per unit area the vehicle exerts on the surface beneath it. Wider tracks distribute weight over a larger footprint. Lower ground pressure means the vehicle is less likely to exceed the terrain's load-bearing limit and sink. This principle works on soft soil, loose sand, and shallow snow. It has a hard boundary. When the substrate transitions from soft solid to liquid matrix, when there is no surface to distribute weight onto ground pressure, becomes a meaningless metric. The vehicle is no longer interacting with a surface. It is submerged in a medium. And no tracked vehicle, regardless of how wide its tracks or how light its construction, generates useful forward thrust when submerged in liquid mud. Soviet engineers understood this boundary. The problem they were solving was not a soft terrain problem in the conventional sense. It was a fluid medium propulsion problem. The vehicle needed to generate thrust not from contact with a surface, but from interaction with the medium surrounding it. That shift in framing from surface traction to medium displacement changed the category of solution entirely. The machine they produced was designated the ZIL 2906. It carried 2 crew members on an open frame, with no enclosed cab and no conventional drivetrain. Its entire propulsion system consisted of 2 large helical screws mounted parallel to the direction of travel, one on each side of the frame. Each screw was a continuous helical blade wrapped around a central cylinder, the same geometric form as a drill bit, scaled to vehicle size. When the cylinders rotated, the helical blades interacted with whatever medium surrounded them: mud, water, snow, wet, tundra, and displaced it rearward. The reaction force pushed the vehicle forward. No wheels, no tracks, no ground contact of any kind. In loose, dry sand, the ZIL 2906 moved slowly. The medium offered limited resistance to the helical blade, producing modest thrust. In soft mud, thrust increased. In liquid mud and shallow water, the conditions that stopped every other vehicle, it reached its maximum operational speed. The denser and more viscous the medium, the more resistance the screw blade encountered, and the more reaction force it generated. The relationship between terrain degradation and vehicle performance was not inverse, as it is for every conventional vehicle. It was direct. The screw performs best exactly where every other vehicle stops. But take it onto a paved road, and it destroys itself in minutes. The operating principle of the screw is not friction. It is displacement. A conventional wheeled or tracked vehicle generates forward motion by pushing rearward against a surface. The surface pushes back Newton's third law, and the vehicle moves forward. This requires the surface to be solid enough to resist the applied force without deforming. When the surface deforms faster than force can be applied, when the wheel or track sinks before it can push, traction is lost, and forward motion stops. The helical screw operates on a different physical interaction entirely. The screw blade doesn't push against a surface. It pushes against the medium surrounding the cylinder, the mud, water, or slurry through which it rotates. As the blade rotates, it drives the medium rearward along the helical path, the same way a drill bit drives material up and out of a hole as it advances. The medium flows along the screw's helical geometry and exits behind the vehicle. The reaction force of that displaced medium pushes the vehicle forward. The process is continuous, three-dimensional, and requires no solid contact surface at any point. The key variable is medium resistance. A screw blade rotating through air displaces almost nothing and generates almost no thrust. Air offers negligible resistance. Loose dry sand offers more. Liquid mud offers significantly more. Water, despite being less dense than mud, offers consistent resistance across the full blade surface and produces reliable, sustained thrust. The ZIL 2906 was fully amphibious, not as a secondary capability, but as a direct consequence of its propulsion physics. Water was simply another operating medium. The transition from swamp to open water required no configuration change. The screws kept rotating. The vehicle kept moving. Steering was equally direct. The two screws rotated in opposite directions, one clockwise, one counterclockwise, which canceled the rotational torque each would otherwise apply to the vehicle frame. To turn, the operator varied the rotation speed between the two sides. Increasing speed on the right screw while reducing speed on the left generated a turning moment to the left. The control logic was identical, regardless of whether the vehicle was crossing mud, water, or snow. The medium type didn't change the steering response. This was not a trivial advantage. Vehicles that use differential track tension for steering, the standard approach on conventional tracked platforms, lose precise steering authority when track-ground contact degrades. The ZIL 2906 had no track-ground contact to degrade. Its steering authority was independent of terrain condition. The ZIL 2906 remained in service with Soviet and later Russian space recovery teams through the 1990s. It was used in documented recovery operations across multiple Soyuz missions where primary helicopter recovery was unavailable or delayed. Its crew of two operated from an open frame with minimal equipment. The design prioritized access to the surrounding medium over crew comfort. In Siberian autumn conditions, that was a significant operational constraint. The vehicle that could reach cosmonauts faster than anything else offered its own crew almost no protection from the environment it was crossing. The same machine that recovered cosmonauts from Siberian swamps was formally evaluated by Soviet military engineers and rejected, not because it didn't work, because it worked only in the one place no army wants to fight. Military utility requires a vehicle to cross multiple terrain types under its own power. A unit can't carry its transport vehicle to the edge of the swamp and then switch platforms. The ZIL 2906 couldn't self-deploy. On gravel, frozen ground, or any surface harder than soft tundra, the helical screw blades contacted solid material directly and suffered rapid mechanical destruction. The same blade geometry that generated maximum thrust in liquid mud was structurally incompatible with hard surface contact. The vehicle had to be transported to its operating environment by a carrier, a truck, a helicopter, or a larger vehicle. For military operations, that logistical dependency was operationally unacceptable. For the specific mission it was designed for, nothing else has replaced it. Screw-propelled vehicles remain in active use for Arctic pipeline inspection, wetland environmental response, and Antarctic logistics support. The operating principle has not changed since the ZIL 2906. Modern versions carry enclosed cabs, more efficient powertrains, and refined screw geometry. The physics beneath them is identical. Helical displacement generates thrust from the medium. The worse the terrain, the more thrust it generates. Every vehicle ever built is limited by the terrain beneath it. This one was designed for terrain that has no bottom. In that terrain, the conventional rules of vehicle mobility don't apply, and the machine that understands that has never had a competitor. The machine was designed for terrain that defeats everything else. In that terrain, nothing has replaced it.